Hi, welcome back to Moose and Chemistry. This is Electron Configuration of Zirconium, ZR lesson. When I look at zirconium on the periodic table, it's element number 40. So let's go ahead and put 40 up here for the atomic number. All right, and now the atomic mass number of zirconium is going to be 91. All right, so now, since zirconium has an atomic number of 40, it's got to have 40 protons. That's right. And since zirconium is electrically neutral, it's going to have 40 electrons. What about the number of neutrons? Well, you just go AMU, yeah, right, minus protons, eh? Okay. And then we're going to go 91 minus 40. Hey, if I check my math, that should be 51 neutrons, right? Pretty darn snarly, that's what I say. Snarly's, by the way, is a new cool. You didn't know that. All right, let's clear some space here because I don't like to leave all that stuff there. Okay. Now, so let's do our electron configuration. Oh, before we do that, we have to remember that S subshell can hold 2 electrons, the P subshell can hold 6 electrons, the D subshell can hold 10 electrons, and yes, the F subshell can hold 14 electrons. And we're going to use the off-ball principle, which clearly states that the lower shells have to be filled before we fill the upper shell. And we're going to use something called the diagonal rule to do so. All right, so here's our diagonal rule. Let's go and get started, right? Hey, 1s2. Oh man, this is amazing. See how easy this is going? 2s2. Wow, it's just going pretty darn snarly. Remember, snarly's cool. 2p6, 3s2. All right, 2p6 and 3s2. Now we got to use up 40 electrons, right? We're going to go 3p6, 4s2. 4s2. 3d10, 4p6, and 5s2. Whoa, whoa, whoa. Pretty cool, huh? So we got 3d10, 4p6, and 5s2. And I've already drawn my arrow to the 4d, it looks like. And so that means it's going to be 4d. If you add up all those electrons, that will give you 40. Now, what about the orbital notation? Well, I use this Hund's rule. Hund's rule says that in every orbit, you have these suborbits. So you have to put an up arrow at every suborbit of that orbit before you put the down arrow for that suborbit. What does that really mean? Watch. 1s, up and down. There you go. 2s, up and down. Here's something easier to see. 2px, 2py, 2pz. So we go 1, 2, 3, 4, 5, and 6. That is just amazing. That's Hund's rule there. 3s, up and down. See, 3px, 3py, 3pz. They're all going up. Now let's start the down arrows. Look at that. Hund's rule in action. 3dx squared minus y squared, 3dxy, 3dyz, 3dxz, and 3dz squared. Let's go and do those. Whoa, look at this. Look how easy this is. And we're just going to use up a total of 40 arrows, right? Plus 40 arrows means 40 electrons. Pretty amazing. 4px, 4py, 4pz. All right, let's start our down arrows. Cool. 5s, up and down. And now, let's look at 4dx squared minus y squared, 4dxy, 4dyz, 4dxz, and yes, 4dz squared. So watch this. Up and up. Well, that's it for orbital notation. What about noble gas notation? Well, you know what? The nearest noble gas to zirconium is going to be Kr. And when I say zirconium, I think of those zircons and those big diamonds, Yeah, don't give your girlfriend one of those. All right, guys, now watch this. Our valence shell right here is going to go right there. Hey, look, honey, I got a zirconium diamond for you. It's 5 carats. Yeah, that's going to go real well. 4d2, 5s2. When I think of zirconium, I just get those diamonds. Anyway, let's look at our quantum notation. That deals with Pauli exclusionary principle, right? So the Pauli exclusionary principle says that no two elements can have the same set of quantum numbers. Well, when you look at zirconium, you look at it and say, oh, it's in period 5. No, it's not, because remember that zirconium is in the D block. Although it looks like it's in period 5, you have to remember the D block is in -1. So you can go 5 minus 1, which is 4. Oh, so our principal quantum number is going to be 4, not 5. That's right. And since it's in the D block, the angular momentum number will be 2. And our magnetic number is going to be -1, because you can count over, like, say, -2, -1. It's the second element over, right? It's located somewhere right in this general area right there. So you're going to put -1. And let's look at our last arrow. Our last arrow tells us it's going up. So that means the spin number's got to be 1/2 positive. Okay, that's it, guys. Remember, be snarly, and we'll see you back here at Musin Chemistry.